Hi guys, welcome back to my channel. Today's video is going to be the Chemistry 30 Thermochemistry unit, and I'll be going over all of the major concepts that will be found within this unit. So I hope you enjoy the video. So for the Thermochemistry unit corresponding to the Chemistry 30 data booklet, it gives us a table on pages 4 and 5 for the standard molar enthalpies of formation at 298.15 Kelvin. So yeah, it gives us a bunch of names of compounds, and it gives us the kilojoules per mole value. So if we want to find like the just the kilojoules value for this delta H or enthalpy, then we could just multiply it by the moles of the substance that we're using in a question. So the page before this one on the data booklet also has a bit of information, and it just relates to the specific heat capacities of a couple miscellaneous elements like air, polystyrene, calorimeter, copper, aluminium, iron, tin, water. So the keystone concept of this whole unit is that the change in energy of the universe is equal to zero. So what this means is that the energy of the system plus the surroundings is equal to zero, and that can also be written as the change in energy of the system is equal to the negative change in energy of the surroundings. So this is important because, like, for example, in calorimetry, the energy that you put in to like heat up a specific metal or water is going to be the opposite of the surroundings, like water, which will be cooled down based off of that. So here's the first formula, and what it does is it calculates the thermal energy transfer between the system and the surroundings of a specific element or compound. So the temperature final minus the temperature initial, or just change in temperature. And here is a C value, so it's different for everything that we use in this unit. So like for example, the water's C value is going to be 4.19 joules per grams degrees Celsius. You could also rewrite that as just 4.19 kilojoules per kilograms Celsius. So that's the same thing. And mass, depending on whether you use this formula in grams or kilograms, you would have to use the mass value in the units of kilograms or grams that would cancel out with this. As well, you could write the Celsius as K if you used the K value for the temperature, if you're using unit analysis to solve these questions. So just to show you how the units cancel out in unit analysis, it's going to be mass in kilograms. Specific heat capacity is kilojoules per kilogram delta C, degrees Celsius, times temperature change, which is in degrees Celsius. So how it works here is that Celsius cancels out, kilograms cancels out, leaving us with kJ as our heat unit. So, whenever a temperature change leads to a phase change, like solid to liquid, liquid to gas, gas to solid, solid to gas, you have to account for another Q value called the uh it's called the phase change or the heat of fusion or vaporization or sublimation. So there's three kinds of movements that particles have. Vibrational is in solids, rotational is in liquids, and translational is in gas. So all of these changes change the potential energy that's in the substance because kinetic energy is the highest in like gas, lower in liquid, and lowest in solid. So the kinetic energy gets changed into potential energy when like you go from a gas to a liquid or a liquid to a solid. When you go from a solid to a liquid, then the potential energy becomes kinetic energy. So here's the formula that you use for this. N is going to be the moles of the substance, and delta H is going to be the heat of like either fusion or vaporization. You can write those as the subscripts, and these are going to be in joules per mole. So you have N, which is mole, times joules per mole. Moles cancel out, leaving you with J as your joules for the unit of energy. So when it refers to molar heat of fusion or vaporization, it just means the amount of energy that is required to convert 1 mole or liquefy 1 mole of a substance at, to the next phase. Sublimation is a bit different where enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization, because how it works is that sublimation is when a solid goes straight from a solid to a gas. So like say we had a solid here. So this would be its like uh the point at which it vaporizes, and this is going to be the point where it freezes or solidifies. So if it goes straight from here to here, it would be like this, right? So it would be this section plus this section equals this section. So just a bit more on phase diagrams. So this is going to be time, this is going to be the temperature. So you have a calorimeter, for example, two substances. Let's say this is substance 1, this is substance 2. So substance 1 and substance 2 reach temperature final. Substance 1, let's say it just cools, we should have that as a straight line. So it just cools down to temperature final. Whereas substance 2, maybe it's a solid state first. So it gets heated up to the melting point. That would be the molar enthalpy of like fusion. Then it goes up. Say this is the boiling point. So it's gonna molar enthalpy of vaporization turns into a gas at the final temperature. So here we're gonna be talking about the difference between enthalpy change, and molar enthalpy change. So enthalpy is the easiest, it's just H, and it's just the measure of energy in a system. So the total energy. Enthalpy change is delta H, so the final enthalpy of a system minus the initial. And molar enthalpy change is also going to be delta H, and it means the same thing, except it refers to when 1 mole of substance goes under a reaction. So it's a bit different. Whereas it's going to be like kilojoules per mole, whereas this one is going to be just kilojoules. So another thing to keep in mind is for an exothermic reaction. So that means heat is given off by the system. So that means if heat is given off by the system, the final heat that's contained within the system is less than what was originally there, because the original gets put into the surroundings, and H refers to the amount in the system. So that means H final is smaller than H initial, and that means that the delta H is going to be a negative value. Now,